On December 15th and 16th, 2025, the James Webb Space Telescope pointed its mid-infrared instrument at an interstellar comet that had just passed closer to Mars than the Moon is to Earth, survived a close approach to the Sun, and was now racing back outward into interstellar space at 68 kilometers per second. The comet was 3I Atlas, the third object ever confirmed to have entered our solar system from another star system. And in those 2 nights of mid-infrared observation, JWST collected something that no telescope had ever collected before, the first mid-infrared chemical fingerprint ever taken of any interstellar object. What it found inside that fingerprint rewrote what scientists thought they knew about both the chemistry of interstellar space and the history of life's building blocks in the universe. The comet had not simply passed through our solar system, it had been altered, processed, transformed, rebuilt at its outer layers by billions of years of galactic cosmic ray bombardment during its journey between the stars. And the chemistry that JWST measured in its coma, in the gas streaming off its nucleus after perihelion, was the chemistry of a universe far older and far more violent than the frozen pristine sample scientists had hoped to find when they first detected this visitor from another star. The 2-observation JWST campaign on 3I Atlas was not a single moment. It began on August 6, 2025, when JWST's near-infrared spectrograph instrument observed the comet before its perihelion passage, before it had reached its closest approach to the Sun. Those pre-perihelion observations revealed a coma dominated by carbon dioxide and carbon monoxide, with water present but not yet the dominant volatile. During the December 2025 observations, Webb collected its first ever mid-infrared chemical fingerprint of an interstellar object. The December observations, taken with JWST's MIRI instrument on December 15th, 16th, and 27th, captured the comet post-perihelion after it had completed its closest solar approach on October 29, 2025, and was now moving outward. The December 2025 JWST MIRI observations revealed the first detection of methane and a reduction in overall outgassing from spectroscopic measurements of 3I Atlas. The methane detection was extraordinary. Methane ice sublimates at approximately 30 to 40 Kelvin, temperatures so cold they only exist in the outermost frozen reaches of a solar system, far from any stellar warmth. Finding methane in a comet post-perihelion, after it had been warmed by the Sun to well above methane's sublimation temperature, required that the methane was being released from depths inside the nucleus that the solar heating had not yet fully penetrated. The interior of 3I Atlas was still releasing the chemistry it had formed in the extreme cold of another star's Oort cloud equivalent, even after being warmed by our own Sun. The discovery that transformed the scientific understanding of 3I Atlas arrived not from JWST alone, but from an analysis published in early 2026 that synthesized the JWST chemistry data with an entirely different dataset, measurements of the comet's polarization properties, the extreme negative polarization detected by the APJL paper from Zuri Gray and colleagues, and the pattern of CO and CO2 abundances that contradicted what was expected from a pristine interstellar comet. The team found that Comet 3I Atlas's extreme abundance ratios can be attributed to the comet being pummeled by galactic cosmic rays, high-energy charged particles, as it cruised through interstellar space. Galactic cosmic rays are the highest energy particles in the universe, charged particles accelerated to enormous energies by supernovae, pulsar wind nebulae, and other violent events throughout the galaxy, then propagating through the interstellar medium at close to the speed of light. During 3I Atlas's estimated billions of years of travel through interstellar space, these cosmic rays bombarded its surface and penetrated deep into its nucleus. At the energies cosmic rays carry, they do not simply ionize atoms or break molecular bonds. They drive chemical reactions deep inside the comet's ice matrix, converting simpler molecules into more complex ones, and specifically converting carbon monoxide, CO, into carbon dioxide, CO2, through a process called radiolytic conversion. The depth to which this processing penetrated is quantified in the 2026 paper. The cosmic ray-altered layer of the comet's nucleus may be 15 to 20 meters thick. 15 to 20 meters of chemically transformed material built up over billions of years of cosmic ray bombardment, encasing a pristine interior core that still contains the original chemistry from 3I Atlas's formation around another star. This layered structure, a processed outer crust surrounding a pristine inner core, is visible in the JWST data as a transition in the chemistry of what the comet releases as it warms. At large distances from the Sun, when only the outermost layer is warm enough to sublimate, the gases released are dominated by CO2, the product of cosmic ray processing. As the comet approaches the Sun and deeper, warmer layers begin to sublimate, the released gases shift toward more CO, toward more water, toward the chemistry that was frozen into the comet when it originally formed. The JWST observations captured this transition in real time, measuring the comet's chemical output at multiple points along its solar approach and retreat. 3I Atlas's activity was dominated by CO2 at heliocentric distances greater than 3 AU, which was later overtaken by water sublimation when closer to the Sun. The comet's chemistry changed as it warmed, the outer processed crust releasing CO2 at distance, the warmer inner layers releasing water near perihelion, a chemical stratigraphy that the JWST data mapped across the full sequence of observations. The cosmic ray crust discovery has implications that extend far beyond the specific chemistry of 3I Atlas. It means that any interstellar object that travels through the galaxy for a significant fraction of its existence will have a chemically altered outer layer. The pristine material that scientists hope to sample, the original building blocks of a planet-forming disk around another star, preserved intact since the formation of that star's solar system, is not at the surface of an interstellar comet. It is buried beneath meters of cosmic ray process material that does not represent the comet's original composition. This has direct implications for the interpretation of Oumuamua, the first interstellar object discovered in 2017, whose anomalous acceleration as it left the solar system has been debated ever since. One hypothesis for Oumuamua's acceleration, proposed by researchers Jennifer Bergner and Daryl Seligman, is that its surface was enriched in molecular hydrogen through cosmic ray processing of water ice, and that this hydrogen outgassed as the object warmed near the Sun, providing a thrust force. The 3I Atlas cosmic ray crust discovery provides the first direct observational evidence that cosmic ray processing of interstellar objects is real, significant, and extends to depths of 15 to 20 meters. Bergner and Seligman's hypothesis for Oumuamua's behavior, cited explicitly in the 3I Atlas processing paper, gains substantial plausibility from the 3I Atlas data. China's Tianwen-1 Mars orbiter added a perspective that no other instrument in the solar system could have provided. China's Tianwen-1 Mars orbiter captured and released new images of 3I Atlas taken from roughly 30 million kilometers away during the comet's October 3rd pass near Mars. The images, a sequence showing the central coma as a fuzzy point moving across the field over approximately 30 seconds, documented the comet at its closest approach to any planet during its entire solar system transit. The China state outlets described the sequence as showing clear cometary features and marking one of the closest probe-based 44 looks at the object to date. The observation was described as doubling as a technology pathfinder for China's upcoming Tianwen-2 mission. The ESA ExoMars Trace Gas Orbiter and Mars Express simultaneously conducted their own observations from similar distances. 3 spacecraft in Mars orbit, all imaging the same interstellar visitor from the surface of Mars's orbit. A convergence of observational assets that had no precedent in the history of planetary science. The Curiosity and Perseverance rovers on Mars's surface had a theoretical opportunity that the arcs of preprint papers noted with particular interest. Cite Index Chart 3.1. At their respective latitudes, the Curiosity and Perseverance rovers could both observe 3I Atlas at night from the surface of Mars during the period when it was closest to the planet, and the diminishing solar elongation would not prevent surface observations until January 2026. Whether either rover successfully imaged 3I Atlas from the Martian surface, making what would have been the first photograph of an interstellar object taken from the surface of another planet, was not confirmed in official NASA releases as of the time this script was researched. But the fact that the geometry was favorable, that the comet was bright enough and the rovers were operational and pointing capable, makes this one of the most tantalizing unanswered questions from the entire 3I Atlas encounter. The FAST telescope in China, the 500-meter aperture spherical telescope, the largest single-dish radio telescope on Earth, conducted a comprehensive search for narrowband radio technosignatures from 3I Atlas across 4 separate observation dates from October 2025 to January 2026, covering the Mars closest approach, perihelion, Earth closest approach, and a post-Earth closest epoch. No credible narrowband radio technosignature was detected from 3I Atlas after visual inspections, placing constraints on the presence of transmitters above approximately 0.3 watts. The Green Bank Telescope in the United States conducted a similar search across 1 to 12 GHz frequencies during the same period and also found nothing. Breakthrough. Listen, the world's most comprehensive SETI program devoted observing time specifically to 3I Atlas and reported null results consistent with the FAST and GBT searches. The combined sensitivity of these searches means that if 3I Atlas carried any radio-emitting technology operating above a few milliwatts of transmitter power in the searched frequency bands, it would have been detected. It was not. 3I Atlas is a natural interstellar comet. Confirmed by chemistry, confirmed by orbit, confirmed by behavior, confirmed by radio silence. What JWST confirmed when it collected the first mid-infrared chemical fingerprint of 3I Atlas in December 2025 was a picture of interstellar chemistry that changes how scientists think about the delivery of organic molecules to planetary systems across the galaxy. The comet's processed outer crust contains CO2 built from CO through cosmic ray chemistry, the same chemistry that operates throughout the interstellar medium, continuously transforming the volatile ices on any small body that travels between the stars for billions of years. The pristine interior contains the original chemistry of its birth environment. The cold outer reaches of a planetary system around another star have frozen into ice at temperatures close to absolute zero, preserved intact beneath the processed surface for the billions of years of its interstellar journey. And the methane that the December JWST observations detected streaming off the nucleus post-perihelion represents material from that pristine interior reaching the surface as the comet's deeper layers warmed for the first time since its formation. That methane, and the complex organic molecules that the Nature paper of June 22, 2026 confirmed alongside it, came from another star's planetary system. It passed through our solar system. It warmed in the light of our sun. The chemistry it released into the space around our sun as it traveled from Mars' orbit back outward toward the heliopause is the chemistry of a universe that has been exchanging molecules between stellar systems for as long as stars have existed. 3I Atlas did not bring a message from another civilization. It brought something more profound, the raw chemical ingredients of life, assembled in conditions that existed before our sun was born, delivered to our solar system by a visitor that spent billions of years traveling through the dark between the stars, and revealed in its full complexity by the most powerful telescope humanity has ever built.